Thank you very much, Ben. It's really a great pleasure to be with all of you. And we do quite a bit of work with California. The California Energy Commission has funded work in our laboratory. And we work collaboratively with also a number of universities in California, including UC Berkeley and others. What I was asked to do today is to give a short primer on floating offshore wind technology. What does a floating offshore wind turbine look like? Why does it float? How does it float? How big is it? How do you moor it to the seabed? I'll end with showing you some projects that we've done using floating wind turbine technologies. So what you see on my screen is called a semi-submersible floating wind turbine. It's one of many technologies out there. If you look at size, the unit is not small. To give you a sense of scale, I've got a school bus right here where my cursor is. You can see the school bus where the cursor is. So these are not very small units. The current technologies exceed 15 megawatts. There have been turbines in the 22 megawatt range that have been developed. Each turbine can produce enough energy for 10,000 homes or more. Now these units float over the water, and typically we do that when we have deep waters. And the way they float is they have buoyancy in them, air buoyancy, just like a boat would float. This one happens to be a semi-submersible design, and it's got 3 flotation columns on each corner and a central column that holds up the tower and the turbine. What makes it float is that there's air inside, so the air makes it float, just like it displaces water and therefore floats. The units are typically moored to the seabed to keep them on station, and typically mooring lines are used. And you can see in this case we have 3 mooring lines, one on the left, one on each corner, one in the center, one on the other side. And what you see coming out of the unit is actually a dynamic cable, is electrical cable that brings the power back to shore. And the cable comes from the turbine down the tower and comes out typically through the bottom of the turbine. And notice the electric cable does what we call a lazy S wave. There's buoyancy modules on the cable to make it do this S wave, and eventually it's fixed to the seabed and connected to other cables. But the reason we do that is the turbine actually moves because it's moored to the seabed, just like when you have a boat. And when you moor a boat, as the wind direction changes, the boat will move around. In this case, we have a vessel that's moved with 3 mooring lines, so you can move around through what we call a watch circle. And that could be a 50 or 100-foot diameter watch circle. So to prevent the electrical cable from breakage, we have this lazy S wave, so the cable can follow the hull as the hull moves around. So that's the anatomy, if you wish, of a floating turbine technology. Now, why floating wind? As I said earlier, we have deep waters off parts of the U.S. coast. Roughly 2/3 of the U.S. Waters within 50 miles are in deep waters, more than 150 feet in depth. That requires floating turbines. What you see off the U.S. coast here is the light blue areas are areas where you have shallow waters, less than 150 feet, where you can actually fix the turbine to the seabed. The dark blue areas are areas that are deeper than 150 feet, where you actually would require the unit to float because it's too expensive to fix it to the seabed. And that's where you would use floating technologies. So notice the Gulf of Maine, where we are, is very deep waters, or pretty much are dark blue. And both the entire West Coast is blue, that dark blue, which is deep waters. Now, if you go to the mid-Atlantic states, and you could see a lot of light blue areas, so you could use fixed bottom turbines in those areas. And then the industry on the East Coast started with fixed bottom turbine technologies. But in the future, we see floating as being where we would go. Maine and the Gulf of Maine and California are the biggest markets for floating wind right now, at least the most likely to be the first to put floating turbines in the water. Now, we test wind turbines technologies in our laboratory to make sure they hold up over 20 or 30 or 40 years. Here's an example of a wind blade being tested in our laboratory using fatigue loading. And these are the kinds of tests are typically done before a new technology is approved to be placed out there. And these tests will last typically 3 to 4 months, maybe 5 months, and represent over 20 years in service. We also have built wave wind basin technologies, basins to actually test floating turbine at scale. And this is we call the W2 wave wind basin at the University of Maine. You could see a floating turbine in the background, an open jet wind tunnel above, and a wave basin at the bottom. So we can create waves and winds that will allow us to subject the units to extreme events and compare that to our models predicts before we put anything out there in the ocean. So there's ways to develop the engineering and the technology and test it and validate it before anything goes out there. Here's an example of our wave wind basin where we're testing at 150 scale. So this is you could see the waves and the wind tunnel above that, and you could see the size of the waves are scaled, of course, to typically 150 or 170 scale. And you could see here a floating turbine in the wave basin being tested to evaluate its performance under, say, 50-year winds or 100-year winds or 500-year winds. So there are tools available to make sure the technology works before we take it out there. So how many different designs of floating turbines out there? There's more than 60 or 70 serious designs out there. There's an international competition to develop better and cheaper and easier to build floating turbine technologies, and you can see a whole bunch of them out there here. But you can actually break them up into 4 different categories. And starting from the left, one is called the tension leg platform. Then there's a barge design, there's a semi-submersible design, and a spar design. And there's different variations of these 4 basic designs out there that are competing in this particular space. The tension leg platform has a body, the buoyancy module filled with air that's under the water, and there's tension legs. These are big cables, essentially, or tension tubes that keep the unit from popping out of the water. All these designs actually are borrowed from the oil and gas industry. The oil and gas industry developed floating oil and gas hulls, and the offshore wind industry and engineers borrowed from these designs and adapted them to floating wind technologies. So this is called a tension leg platform, and if you break one of these tension legs, the whole thing will flop over. The other design that's out there, it's called the barge design. In its name, it looks like a barge that holds up the turbine. Until recently, people didn't believe that would work, but we have technologies now to make that work. And then the semi-submersible design is the most common design being used right now for floating wind. I described that a bit earlier. In this case, you have 3 different flotation columns on each, and then a tower in the center, and mooring lines, as you see, that keep it on station. And finally, the last design is called the spar design. The spar design is like a big floating tube that has a ballast at the bottom of the tube, but the rest of the tube has air in it. And the ballast at the bottom of the tube keeps the tube straight up. It is the least expensive design. In many cases, however, it has major problems with deploying it, because typically it has a draft of over 250 or 300 feet. So it's very difficult to find a port facility from which you can deploy a unit like that. So these are different designs. There's different variations of these designs out there. Where are we in the Gulf of Maine? In the Gulf of Maine, the Bureau of Ocean Energy Management last year held an auction, just like you had in California. And that auction was based on these sites that you see in here. And they were all auctioned off. But the way we got to these sites is by looking at birds and bat activities and whales and mammal activities. So there's been a lot of research done to figure out which sites provide the least environmental impact on birds and bats and mammals and other life, and also least impact on the populations that utilize the ocean. But in any case, these sites were selected. They were put out to auction, and then 4 of these sites were actually sold in auction last year in the Gulf of Maine. Now, none of this is going to be built this decade. This will be more likely what happen in the next decade. We have a floating technology roadmap in Maine, where we would like to crawl before we walk and walk before we run to minimize the possibility of mistakes. And this is where there's a real opportunity to collaborate between Maine and California. So what we learn in Maine helps California and vice versa. So back in 2013, about 12 years ago, we deployed the first floating turbine off the US coast. It was a 1/8 scale version of a semi-submersible design. And then in 2025, this year, we deployed, as Ben said, another unit that's a lot more optimized, and we won a national competition to put that in the water. And it's a quarter scale design. I'll show you a few slides on that later. And then the goal here is the next decade, there would be a research array in the Gulf of Maine that would be roughly 10 to 12 turbines. And that research array would help us collect a lot of data on not only the mechanical performance of these systems, but the impact on the environments, the birds, the bats, the mammals, and so on and so forth. And that would be an opportunity for Maine and California to work together again and learn together of how this research array not only performs, but also how it impacts the environment around it. And then following that, hopefully in the 2033 plus time frame till the end of the decade, we could see potential commercial developments in the Gulf of Maine. So this is the very first turbine we deployed back in 2013. You could see the hull being towed out to sea. Notice there's 3 flotation columns, 1 in each corner. And these are concrete units filled with air. It's not concrete that floats, it's the air inside the concrete that makes it float. And notice how stable it is as you tow it out to sea. This was a quarter scale design that we developed and towed out to sea. And then when we arrived to the site, there were pre-installed mooring lines and anchors, and we attached it to the mooring line and anchors. We had pre-installed electrical cable to shore, and we connected the electrical cable to the unit. This is what the site where we deployed it 12 years ago off the coast of Maine. It's in Castine, Maine. It's a beautiful site. There's a lighthouse right there, and this is the location of the hull. But there, you can see there's 3 buoys, 1, 2, and 3. That shows the location of the mooring anchors. So there's mooring lines that go from the hull to these 2 anchors at the bottom of the sea. I'll show you what those look like a little later. We also deployed a floating LiDAR system to measure winds and wave environments and measure acoustic sounds from mammals under the sea as well. And this is what our first extreme storm looked like. It was a 50-year storm, a return period storm that occurred on December 15th, 2013. Needless to say, the engineers who designed that didn't sleep the night before very well. But we had 50 sensors on board to see how it performs. Notice here the white caps and the relative size of the white caps to the hull itself. And that represents 50-year storms. And notice that you can't see the hull move in a 50-year storm. And that's really what we wanted to show, is that we have designs that are stable enough that will withstand 50 and 500-year storms and still perform very well. And again, that was part of the experiment, and it was very successful for us and proved that this technology can withstand the major storms. To give you a sense of scale, a 50-year storm in the Gulf of Maine has waves about 60 feet high. And a 500-year storm would be roughly 70-foot waves. How do you moor these to the seabed? Again, there's different mooring anchors and mooring lines. So at the bottom of the sea, there's an anchor, and the anchor is attached to a mooring line to the hull itself that keeps it on station. As I said, typically we use 3 mooring lines, but oftentimes we'll use 6 mooring lines depending on the soil conditions. There's different kinds of mooring systems or anchors. The first one you see on the left is a dead weight, a very big mass, essentially, typically made out of concrete. They're used in typically shallower waters. You can have driven piles into the seabed, or drag anchors. These are anchors that are dragged onto the seabed. They embed themselves, and then you can't pull them out anymore unless you pull in the other direction. If you get to deeper waters, like you have in California, more than 400 meters deep, then you go to either suction piles that you see in number 4. A suction pile is like a big tube, and then you pull water out of the tube and it embeds itself into the seabed. You could have torpedo piles that are driven into the seabed at high speed, or you could have, again, vertical load anchors or drag anchors. And so there's different ways to anchor the mooring line into the seabed, depending on the type of geophysical conditions or water depth that you have. Now, what does a mooring line look like? The most common types of mooring lines were metal metal rings like that, so basically steel chains. But these are not tiny chains. That you could see this is a 6-inch diameter chain that's 3 feet long. So it looks like almost the size of a desk. If you have a desk that you're working on, so it's a very big unit. But these are very heavy and difficult to handle. And more recently, over the last few years, the industry has been moving to synthetic mooring lines. These mooring lines are a lot lighter, about 1/20th the weight of a steel anchor, and you can actually wrap them on a drum and take them out to sea and deliver them into the seabed. And then of course, at the end of a mooring line, there's an anchor, like I showed you earlier. So on one end of the mooring line, there's the anchor on the seabed. On the other end, the mooring line is attached to the hull itself, and that's how the hull stays on station. Now, when we design a hull like that, how do we know, are there criteria for designing it, and do we follow criteria? Actually, there are international criteria as well as US criteria for designing these hulls, so they will survive over 500 years. The American Bureau of Shipping, who actually has criteria for floating structures, oil and gas rigs, and boats, and so forth, has also criteria for designing floating wind hulls. And typically, when we design a hull, we design for extreme storms, both waves and winds. We design for ice if you have, you're in an ice location, ice impacts, for example. We design for currents. And typically, we design for combinations of these different loads. Typically, a single design might have 80,000 different load simulations or load cases that we design for. And what you see here, an example of a hull moving, the movement is being magnified right here using a numerical model of the hull. And what you see at the bottom are the stresses the hull sees inside the structure. And that's how we design it to make sure it's strong enough so it doesn't break in the water over the long run. In terms of the electrical lines, I talked about that a bit earlier. But in deeper water, such as in California, electrical lines present challenges because you may have 2,000 to 3,000 feet of water that you have to put the line in, and so the line has a long ways to get to the sea floor. In shallower water, like we have in the Gulf of Maine, like in 300 feet of water, what we would typically do is we bring the cable down, as I said earlier, and then it comes out of the hull using a J connection to keep it from fatiguing at that intersection. And then we have buoyancy modules that are attached to the hull. They're like flotation modules that will bring the cable back up, essentially. And then the cable is brought back down, and then there's a tether that's placed in the seabed and an anchor. And the cable goes through the tether, and it could be connected to another cable, to a turbine nearby. You can daisy chain them, and then when you have multiple turbines in a farm, typically every 5 or 10 turbines cables are come together to one collection point, and then groups of 10 turbines are connected to another offshore connection point, and then you have typically an export cable back to shore. And the export cable brings, so you only have typically one export cable. Oftentimes it's doubled up in case one of them breaks, but it's a single export cable that goes from a farm to shore. But within the farm, there are these smaller cables that connect the turbines together and back to the export cable. How do you usually bury the cable? The answer is yes. You try to bury the cable if you can to keep it from getting snatched by fishing operations and others. And typically you run a cable survey. This is an example of a cable route survey that we've done in the Gulf of Maine. And you can see in brown, these are rock outcrops. In the Gulf of Maine, we have a lot of rock outcrops. Typically, what we thought initially, we'd put the cable in this location. After we've run the survey, we actually move the cable out to another location to where there's mud pockets. And typically, you want to bury the cable in the mud 5 or 6 feet. And if you can't bury it, if it goes over rocks, you typically cover the cables to protect it from snagging operations. You cover them with concrete blankets that are made with smaller pieces of concrete that will protect the cable. But you really want to bury it if you can. So that's how the cable brings the power back to shore, in essence. And then these electrical cables, you ask yourself, are they new? Is it new technology? The answer is no. We've been using electrical cable to connect the mainland islands in the United States to the islands to the mainland to bring power to the islands, and we've been doing that for a long time. In the Gulf of Maine, for example, this is a cable from Northport to Osborough, Maine. It's a island off the coast of Maine, and the cable is buried in the seabed, in the mud between the mainland and the island. It was originally installed in 1955, but then it was severed, and then a new cable was installed in 2015. So it lasted certainly close to 70 years in that location. So this technology for cable is available and knowledgeable. However, properly installing the cable, given it a burial of 6 feet or more, is really critical so it doesn't get snagged. Oftentimes, if there's currents under the water, the currents can actually expose the cable over time because you get the sand, if you wish, or soil is removed from above the cable, and you lose cover on the cable. Cable breakage is an important part of the design of these farms. You want to make sure that you properly design the cables so you don't have outages and repair costs. Finally, I'd like to show you the last turbine we put in the water, that we won a national competition to develop a next generation floating turbine. And you can see it right here off the coast of Castine, Maine, being towed to site. And that hull uses a motion stabilization system. In other words, inside the hull, we have water that moves around and actually negates the motions of the waves. And we do this in California, and in some places in California, you have what we call twin mast apparence in earthquakes. On the very top of buildings in earthquakes, you have a mast that moves back and forth and helps negate the earthquake motions. We're using something very similar on this hull, where we can negate the motions of the waves and the winds. We can make a much smaller hull that's a lot more cost effective. So we call the technology Volturnus Plus. It's made out of concrete. And it's 30% lighter than a typical semi-submersible hull. And the other really big advantage of the technology, we make the whole hull in one piece using what we call concrete slip forming. So there's a form in concrete. When you pour concrete, you have forms. In this case, we have a form that moves up, climbs up the hull as you make it, and you can continuously pour the concrete, so the whole hull is made in one piece. So that's a next generation technology that I think we can collaborate on. Actually, the California Energy Commission funded a project just a month ago at the University of Maine for collaboration between Maine and California using this particular hull technology. And the concern there in California is the impact of with potential wave entanglement and impact of waves and mammals on an interaction with the mooring lines and the fishing lines. So again, there's collaboration already ongoing between our two states to try to answer some important questions before we go out there and start building these farms in large volumes. So that's my contact information. You please feel free to email me or call me if you have any additional questions. But I'm happy to answer questions of various types. So.